We're going to learn about implicit differentiation, which is a technique needed when it's not really easy to solve for y in terms of x. This problem's not so bad, but of course we're going to start simple and then see some that you wouldn't even think of trying to solve and dig what y is equal to in terms of x. So we use this sort of backdoor technique to find dy dx. We're going to use the Leibniz notation to keep everything straight. And what we're going to do is differentiate both sides. So 2x plus 2y, and this is the new part, dy dx equals 0. Alrighty, where did the dy dx come from? Maybe there was a dx over here, but that was just 1. So we didn't really write it, but here we need to write it because of chain rule. We said a minute ago that y is a function in terms of x, and by noting this, we know we need to take the derivative of that input function. So it's like leaving a little post-it note that we'll get to that in a minute. So let's try to isolate it. Let's leave this term here and subtract 2x from both sides, and then divide both sides by 2y, and simplify to minus x over y. So the derivative with respect to y, or excuse me, the derivative of y with respect to x is minus x over y. And if you look back at this formula, it looks like the formula for a circle, and it makes sense that the slope of the tangent line would be dependent upon the values of both x and y, since there would be two tangent lines for those values, one on the top and one on the bottom, varying with the signs of x and y. So, new technique, let's practice something a little more difficult. Here's a formula for a circle whose radius is 3, sketched here, and I plotted the points 2 square root of 5 and 2 minus square root of 5 because I was going to be working with x equal 2. So there will be 2 points on the circle where x has a value of 2, a positive y value and a negative y value. So let's use implicit differentiation to help us write the equations of the two tangent lines that touch these 2 points. As before, 2x plus 2y, and then because of chain rule that y is a function of x, we're going to write dy dx, indicating we have to take the derivative of the input function and then equal to 0. Solving for this term, we're going to get dy dx equals minus x over y. And that's going to be Rm to help us write the linear equations of the two tangent lines. So we're going to have dy dx, and our little stick is going to show us at the point 2 square root of 5 and at the point 2 minus the square root of 5. So let's solve for that. Minus x over y would be minus 2 over the square root of 5 for a slope on the first line, and minus 2 over minus square root of 5, or 2 over the square root of 5 as a slope on the second line. Now let's put these two pieces into point-slope form with the accompanying point values and see what our equations of tangent lines are. To finish the problem of the circle x squared plus y squared equals 9 and finding the tangent lines when x equals 2, I'm taking the liberty to do all the algebra here and even render a decimal approximation, because this is just a review of algebra. I use the point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. And I added in, or inserted, the appropriate y1 values, x1 values, and the slope associated with that particular point. Likewise, down here, I have a different y value, same x value, because there are two x's for those, or two y's without one x, not a function. And same technique down here. The first one cleans up sort of not so pretty in radical form. So a decimal approximation would be y equals negative 0.89x plus 4.02. And the other one, again, not so pretty in its radical form, but roughly approximating decimal form, 0.89x minus 4.02. So interesting characteristics shared by the two lines. I've sketched them in green up here, showing that they touch both of these points, and their slopes hopefully make sense to you from the equation. This is a negative slope as it appears. It matches, and it's almost a slope of -1, so we can see that that makes sense. Its intercept is y equals 4 up there, and this one has sort of the opposite slope. It is 0.89 but positive, and intercepts at a negative 4.02 down here. The two lines intersect as well, and that's a whole nother little algebra activity. But the usefulness of implicit differentiation was in finding the slope that enabled us to find the equations of both tangent lines. Let's do a little more implicit differentiation practice. Let's try our new technique on x cubed plus 2xy minus y squared equals 3. 3x squared plus, and notice here we have product rule to do because we have two variables, two functions. Remember that y is a function of x. So let's treat it with the respect it's due. Let's call the first function 2x. So the derivative of that is going to be 2. And with the product rule, we leave the second function alone. Then we add to that the first function left alone times the derivative of the second. Post-note time. The derivative of that function is dy with respect to x. Continuing on, we know to bring the 2 down, and then chain rule kicks in. Y now has an exponent of 1, but a composite function, a function built of x's. The derivative of that function with respect to x must be taken eventually or found using implicit differentiation. Equals 0. This time around we have two terms containing dy dx. So let's leave them on the left side. And while we're at it, let's factor out that dy dx, knowing that we'll then have 2x minus 2y, and subtract out the other pieces, minus 3x squared minus 2y. And lastly, solving for dy over dx, or derivative of y with respect to x, the function we're not trying to solve for, but come in the back door, so to speak, and find its derivative. Lastly, by dividing out this unwanted factor. So minus 3x squared minus 2y over 2x minus 2y. Or if you want it a little prettier, 3x squared plus 2y over 2y minus 2x, achieved just by multiplying numerator and denominator by minus 1 times minus 1. And there you have it, another way to practice implicit differentiation.